Yeah. So, hello and welcome everyone. I'm thrilled to be here as your host for today's teaching session. My name is Pranshul Akhotia, and I'm excited to introduce you to our amazing speaker, Abhishek Ghosh, a core team member of a prestigious society, CodeChef NSUT. But before we dive into the lesson, I want to take a moment to tell you about our society, CodeChef. CodeChef is a group of passionate students who are dedicated to improving their programming skills and competing in coding challenges. Our society provides a platform for students to grow their skills as well as compete with other programmers from around the world and increase their rating on online coding platforms. So, without further ado, let's get started. I'll hand it over to Abhishek sir to teach us all on the topic segment trees.
So, hi everyone, this is Abhishek, and thanks Pranchi for the lovely introduction. I'll quickly present my screen and we'll start. Is my screen visible, Pranchu?
Yes, yes, we are.
Okay, so before we start, so segment tree is basically a very useful data structure, a very flexible data structure, I would say, and has many use cases. So it is considered to be an advanced data structure, but I think that it is very basic once you get the idea of it. So before we start, I'll just quickly mention the outline to you of what all we plan to cover in this session. So it will be a 1 hour session, and we'll start off with the basic introduction on segment trees. So in this, we'll cover why we need segment tree, what are the other uses of segment tree, and like that. So this session is planned in such a way that even if you're new to programming and even if you have no, I mean, if you do not have much experience in coding, you'll still have something to take away from this session. And the starting part of the session will completely be mathematical, and if you know basic mathematics, then you will be good to go, I would say. Then after introduction, we'll go through the structure of segment tree or structure of trees. So even if you have not done much of data structure algorithm, you'll still be able to understand as we'll start right from the basics up till intermediate level. So in structure of tree, we'll cover the representation of segment tree. We'll cover the size of segment tree and other mathematical proofs. Then we'll move on to the basic operations that are performed on segment trees. So long story short, the basic three operations that are performed are build operation, update operation, and query operation. My screen is visible, right?
Yes, yes, we are.
Okay,
It's
and then
visible.
we'll discuss code. So code part will not occupy a much large section of the session. Code part will be very small. Okay, so we'll just discuss from a high level the coding part. So more emphasis will be on understanding the concepts. And then in the end, if time permits, we'll also discuss range updates and using lazy propagation and a few advanced examples as well. Okay, so let's start off with an example. Okay, so just understand this problem. You are given an array. Okay, you have an array, and you need to return the sum of elements in the range L to R. So L to R basically is a range query. This is called range query. Whenever you have range queries, there are different approaches to solve this. So there are basically two schools of thought when you're provided with a question of this sort in which you need to return the sum of a particular range. The first one would be the most standard approach, and the second one would be prefix sum. So the first approach would be like if I ask you what is the sum for the range 2 to 4. By 2 to 4, I mean the indices 2 to 4. So L is 2 and R is 4. So the sum of elements would be the sum of this segment of the array. So the sum is 9 plus 6, 15 minus 2 is 13. So the answer for this range sum query would be 13. Okay. So L and R were like this. So this is what your range query is. So the first and foremost, the most basic approach would be to start a loop from 2 and go up till 4 and sum your elements in it, right? So in the worst case, this would be an order of n approach, right? Order of n, or I should say linear time approach for each query. And you're provided q such queries and your size is n. So for this array, your n is 8 as there are 8 elements starting from 0 to 7 index. And for each query, if you're taking order of n time, total time complexity of this approach would be order of q into n. Q is your number of queries and n is your complexity for each query. Okay, so these are your range queries. So this was your first approach. So can we do any better? Okay, sum for L to R is basically your array of L plus array of L plus 1 right up till the last element 8AR. So there are n elements in this, right? So what if instead of adding the single elements, we act a little smart? Okay. So for those of you who are unaware of prefix array is anything which stores the answer from the starting to a particular index. So I'll quickly create a prefix array for this. Okay, so let's fill the prefix array. So prefix array. So if you move from starting index, so pre of I, what is pre of I? Pre of I will be sum of elements from 0 up till that ith index. Okay, so pre of 0 will be the sum of this part of the array, which is 4, right? Pre of 1 will be sum of this part of the array. 4 minus 1 is 3. Prefix sum of 2 would be 9 minus 1 plus 4. Or I can simply just uh, add it. Just give me a second. So prefix sum of 2 would be sum till first index added with this element. So 3 plus 9 is 12. 12 plus 6 is 18. 18 minus 2 is 16. Plus 5 is 21. Plus 7 is 28. 28 minus 8 is 20. So prefix sum of 7 is basically the sum of the complete array. Sum of complete array is 20. Okay, so pre of I stores the sum till particular index, right? So if we just clear this up a bit. So to understand this clearly, prefix sum of I, let's say I is 4. So prefix sum of 4 will store the answer for this part of the array. Okay. So prefix sum of 4 and prefix sum of 1 will be storing this part of the array. So if I subtract prefix sum of 4 from prefix sum of 1, I will get the sum for this part of the array. Right. So sum query can be modeled this way now. So let's say sum of L to R. Initially, what we were doing, we were just iterating from 2 to 4. But now what we'll do, we will subtract prefix sum. Prefix sum of R subtracted by prefix sum of L minus 1. Why L minus 1? Because the range is inclusive. So we need the sum from 2 to 4, which will be the sum from 0 to 4 subtracted by the sum from 0 to 1. So this complete sum subtracted by prefix sum of 1. So prefix sum of 4 is 16 subtracted by 3. So it will be 16 minus 3 is 13, which is same as what we got earlier during using our first approach. So what is the complexity of this approach? The building of a prefix sum array will take order of n time, right? We are just simply just creating an array, iterating from the start right up till the end. So this will take order of n time for building. And for query, we are simply answering each query in constant time. Because see, we have already computed this value, we have already computed this value. All we need to do is subtract, and subtraction is a constant time operation. So sum of L to R was obtained in constant time using prefix sum. So if we just try to summarize a bit, okay, when you are provided a problem like range query in which we need to answer for some particular range, we need to return the answer for some particular range. There are basically two schools of thought. The first one would be to use the standard approach. The second one would be to use prefix sum. And if I just quickly try to summarize the two, if I ask you to query, okay, so querying in standard approach would take order of n time, constant linear time. And prefix sum, we were simply just subtracting prefix sum of r with l minus 1. It was a constant time operation. But now if I ask you to update any particular index, now this update is called a point update. Okay, so if I ask you to change index 3 value to let's say 8, Okay, so 6 changes to 8. Now the array is like this. Now if I update it like this, my still if I was using the first approach of standard approach, it would still take order of n time for query, but the update would be fast. Okay, because we are just simply assigning the value at particular index to the new value. So it is constant time for update, and these updates are point updates, and this is what a point update basically is. At any particular index, feeding a value. But what about prefix sum? If I was using the prefix sum approach, then updates would be linear time, because see, if I'm making change at index 3, so now prefix sum till 2 would be unaffected, like this would be still be fine. But all the values starting from 3 up till the end would now have some wrong value. So I need to update it again. So I need to change all these values. So 12 was the sum till here, which was fine. But since this value was increased by 2, I need to update now. So 18 will change to 20, 16 will change to 18, 21 to 19, 28 to 26, 20 to 22. So in the worst case, if I need to make a change at the starting of the index, starting like a 0, 1 or like initial indices, then I need to make changes right till the end. Okay, so in the worst case, this is order of n operations. So the queries that I am provided, they are of two types. The first was range query, and the second query type of query was update query or point update. So if the value of q is very large, okay, like q is in the range of let's say 10 power 5. So performing order of n operation is something which is not uh, possible, right? This will definitely exceed the time limit, and these are very slow. So I need to do a little better on order of n for both of these approaches. So I need to do better than both of these if there are updates. Now I have changed the question. Now the question involves updates. Now when there are updates, I can not use either of the two. Okay, because if the number of queries, which is q, if it is a fair share of both the type of queries, then both of these approaches are slow and will TLE. So here comes segment tree. Okay, so this is right from the we're discussing segment trees right from the basics. So uh, let's say, okay, so prefix sum gave us an idea that okay, if I do some pre-computation, which is before the queries, if I create this prefix array, or if I store the sum answer for some smaller values or some smaller sub problem, then I can answer the larger values. Okay, so in the first example, I asked you the sum for 2 to 4. Okay, so sum for 2 to 4. In the first approach, it was the sum for 2 to 4. It was a of 2 plus a of 3 plus a of 4 in the standard approach. In the prefix sum approach, it was pre of 4 subtracted by pre of 2 minus 1, which is pre of 1. This was constant time, this was linear time. Now, if I have some smaller values, okay, so if I have answer for let's say 2 to 3, and I have the answer for 4 to 4, and if I take the sum of both these two, then I will land with my original answer which I wanted, the sum for particular range. So using divide and conquer approach, divide and conquer is basically breaking down the problem right in two. So let's say I have this array, and I store the answer for the left part of the array, like the sum of left elements and the sum of right elements separately. Okay, so here I am storing the answer for this first part, and here I am storing the answer for the second part. Then when I merge the two, I will have this part and I will have this part. So I will have answered the bigger problem at hand. Okay, the initial one, by storing the answer to the two halves. So exactly this is exactly what we are going to do. So in segment tree, we are storing the answer for some particular segments. This is the reason it's called a segment tree. Okay, so the segment, and this is the root of the segment tree, the topmost element. Okay, so 0 to 7 is the sum for 0 to 7. I'll just copy the array so that we can. Okay, the array was modified actually, so I'll copy back the array. So we have the array with us. So this was the array we had. Okay, so sum for 2 to 4. So 0 to 7, we have the sum for the complete range, which is 20. 0 to 3, we have the sum for this left half. 4 minus 1 is 3, plus 9 is 12, plus 6, 18. So we have stored the sum for left part, we have stored the sum for right part. Now this will help us to solve the query of 2 to 4. Okay, so now we want the sum for 2 to 4. We check at the root 0 to 7. We do not need 2 to 4. 0 to 7 is not useful to us directly because this is a sum for the complete array. So we check the left part 0 to 3. This is still not useful for me. 0 to 1 is completely outside of what I want, right? 0 to 1 has no relation with 2 to 4, but 2 to 3 I think has some relation with 2 to 4, right? So this is useful for me. So I'll take this value. Then I'll return back. Then I'll return back, and then I'll make check for the right part. 4 to 7 is not completely useful for me, but I think it is partially useful for me. So I'll check this left part. 4 to 5 is still partially useful for me. So I check this part. 4 to 4. Okay, so this is something which is a part of my query. So I return back the answer. And I do not need to check for the right part because it is completely outside. Same goes for here, same goes for here. So I have now have two nodes. This 2 comma 3 and 4 comma 4. So the sum of these two will be 15 plus minus 2, which is 13. This is what a segment tree basically is, as we have stored the answer for smaller problems. Pranshu, is there any doubt in the comment section till now?
No, bhaiya, not till now. No doubt.
Okay, I hope everyone is following. If there's any doubt, you can ask in the comment section. I'll pause and explain. Okay, so answer for 2 to 4. But again, how is this solving our initial problem, right? Our problem was that if there are any updates, we were not able to solve this update problem using prefix sum. Why do we need segment tree? Here is your answer now. If there are any updates, we can perform the update in login time as well. How login time? Just forget that. We'll understand this in depth in the next part of the session. So, okay, so querying is simple, right? I have some answer to some smaller problems and I combine it to get the answer to the larger problem at hand. This is what segment tree basically does, divide and conquer. We are dividing the problem and we are assembling the smaller parts to get the answer to the larger part. So, cool. So what if there was an update, right? At index number 3, there was an update, right? 6 was changed to 8. So how will I do that? See, update is way easier than query. So I move from the top pass. Okay, I'll just change color. Okay, so here, this is not useful for me, right? But I think index 3 lies to the left part of the array, right? 0 to 3. I think maybe it is involved. It needs to change this value. So I'll move here. Okay, 0 to 3. 0 to 1 is outside of what I want, right? I just need to change the value at 3. So I'll move here. 2 to 3. This is still 3 lies to the right side. So I'll move here. So now I'm at this index 3. So I'll quickly change the value. I've changed 6 to 8. Now while returning, I need to make changes, right? 9 plus 8 is 17. So I change this value to 17. Then I return back. Then the answer to this would be 17 plus 3 is 20. Then when I return back, 20 plus 2 is 22. So I have made total of 1, 2, 3, 4 changes just to make a change at particular index. Okay, so since our n is very small, okay, n was 8, you might not understand the power of segment trees. But right now what we did is actually way faster than our prefix sum or standard approach. This the power of segment tree will be appreciated when n is very large, like somewhere in the range of 10 power 5. Okay, so I was if you were paying attention, I was talking about log n. Log n. So bear with me. If I just take log of n right now, when n is 10 power 5, so log of 10 power 5 comes around to be 5 multiplied by log 10 base 2. Log 10 base 2 is something in the range of 3 something. So in the worst case, we will make around 20 changes in the array. And 20 is way smaller than 10 power 5, right? 20 is very, very smaller than 10 power 5. So we have saved a lot of time when the value of n and q is very large. Okay, time complexities and everything will be discussed in greater detail. So for now, if there is any doubt, you are free to ask. Till here, if you're facing trouble understanding anything. Cool. So now we'll discuss the structure of segment tree. Okay, segment tree. So for those of you who have been practicing data structure and algorithm, know that a tree is represented using some node. Then you have pointers to left and right child and something like that. Either you can follow that approach, or what you can do is you can simply create an array. Like those of you who are familiar with priority queues or heaps, this is how a heap is used. Okay, we follow array based representation of tree. Okay, so this array right here, this array, this array is actually our segment tree. Okay, don't believe it, I'll just quickly make sense. If your parent node has the index x, then if we are following one based indexing, which we are gonna do, like zero index is not very useful for us, we start with one. If I quickly number this segment tree, like this segment tree is the same as what we were using in the previous slide. I quickly number the segment tree. The numbers will be one, two. I think blue is not visible. It will be one, two, three, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so I'm using the numbers from 1 to 15. So there are total 15 nodes in the tree for n is equal to 8. Okay, 0 to 7 basically means there are 8 elements in the larger problem. Okay, so n is 8 and we were using total of 15 nodes. So if I represent them using a tree, what would the values be? At index 1 I have 20. At index 1 I have 20. At index 2 I have 18. So quickly just fill this up. At index 3 I have 2. Index 4 I have 3. Index 5 I have 15. 6 I have 3. 4 minus 1, 9, 6 minus 2, 5, 7 minus 8. So we used 1 to 15 to represent our tree. So just understand this. Try to understand this. If I am at this index, okay, index 4. For index 4, its left child is at index 8 and right child is at index 9. So it should immediately be like logical that the left child of the parent will be 2 into x and the right child will be 2 into x plus 1. So this is something which is not related to segment tree only. This is extended, this idea can be extended to all kinds of trees. Okay, and if you're using zero based indexing, then this would be 2x plus 1 and 2x plus 2. Okay, so for the root is index 1. The left child of that root which is storing the answer for the left part of the major array will be index 2. Okay, so index 1, left child is index 2 and right child is index 3. Wait, so taking another example, index 5. So when talking about index 5, the left child of index 5 will be index 10 and right child will be index 11. Okay, which is clear, 10 and 11. This is how a tree is represented in the memory. So in memory, this is how a tree is basically represented. Now when I talk about segment trees, okay, so segment trees basically we are storing the answer to smaller problems. If you look closely, the leaf nodes, what was the problem we are trying to solve? Our problem was of sum of L to R range, which is our range query. So our leaf nodes basically contained the array values only. Okay, sum of 8 comma 8 is basically just a single element, which is the element at index number what do you call it, 0. I think index is 0, sorry, 0 comma 0. So at node 8, node number 8, so node number 8 is basically storing the array value for 0, right? Index 14 is storing the array value for 6 comma 6. Okay, so this is a of 6, as there are single elements, right, single ranges. So when we are combining the two, when you're combining, this is for 0 1 comma 1, when you're combining the two, you basically just take the sum of both these parts and return for the problem when we are using sum. Okay, by the way, okay, we'll discuss prefix sum in greater detail later on. So left child and right child are clear. This is how a segment tree is represented in memory. Cool. Now when talking about height of segment tree, let me just take a few examples and this will be. Okay, so this is the segment tree for n is equal to 8. Okay, segment tree for n is equal to 8. I'll create another copy of it. For n is equal to 8, this is the segment tree that we have. So what's the height of segment tree? So let's say at this level, the height is 0. At this level, the height is 1. this level the height is 2, at this level the height is 3. If you look closely, what is the number of elements at each uh, level? Okay, so at this level we have just a single element, one node basically. At height 1 we have two nodes, at height 2 we have four nodes, at height 3 we have eight nodes. So number of nodes at each level is nothing but 2 power h, which is being the height of segment tree, starting from 0 up till 3. So what is the basically height of tree is this. What are the maximum uh, level till which we can go? So when n was 8, we had h is equal to 3. What if n was 9? Okay, so we would have another node, right? Just increase of a node by 1 from 8 to 9, we have another level in the tree. Okay, so when h was 4, when n was 9, we have h is equal to 4. So height of tree is closely the number of nodes is 2 power h. The leaf nodes is basically the number of elements that we have. This is a leaf node, this is a leaf node, this is a leaf node, and all these are leaf nodes. 7 plus 2 is 9 leaf nodes corresponding to the 9 elements of the array. So if you just take what would be h, right? If n is equal to 2 power h being the number of nodes, then h would be log n base 2 ceiling. So is everyone aware of ceiling and floor? Basically, if n, let's say log n base 2, when n was 9, log n base 2 would come out to be 3 point something something something. Okay. If you take the floor of this value, the floor of this value would be 3. The ceiling of this value would be 4. Okay, basically the nearest integer, greatest integer value for floor, and for ceiling we just take add 1 to it. Okay, the next integer in query. So height of segment tree is this. Now what is the number of nodes that we are using? Okay, so this is a binary tree concept only. If n is okay, let's say if there are n elements, n leaf nodes, then there are n minus 1 internal nodes or inner nodes, or rather I should say non-leaf nodes. These are all leaf nodes, and all these nodes are non-leaf nodes. Okay, so when you have a full binary tree basically means when each node has either zero children, or two children. Okay, so this is a leaf node. This does not have anything below it. So this is a leaf node and has zero children. This is a this is non-leaf node because it has two children, right? This is the analogy that we're going to follow. So in a full tree, if n leaf nodes are there, then there are n minus one inner nodes. Is everyone aware of this concept, or I think it's fine? So the total number of segmentary nodes comes out to be n leaves plus n minus 1 inner nodes, which is 2n minus 1 nodes in total. Is everyone following till here? Are there any doubts?
No doubt be in the chat, Abhi. If anyone wants to ask any doubts, you can speak on the mic as well.
Okay, clear. Clear. So 2n minus 1 nodes are total number of nodes that we're using. So can I create an array of size 2n minus 1 and it should be comfortable, right? Actually, no. Okay. So what would be the size of the array that we're using? Array, basically, when I say array, I'm talking about the segmentary array, which is the R tree only. So long story short, I'll quickly just write down the size of a segment tree should always be at least 4n. Uh, 4n. Now, why 4n? This is actually a mathematical proof, and it's actually very interesting. You find it very interesting. So, the reason I created a copy of this node is because I need to show this again. So, this was for n is equal to 8, right? We were using 2n minus 1 nodes. So far, so good. So, when n is equal to 10, this would store the answer for 0 to 9. This would store the answer for 0 to, or I think should increase the size of this. Okay, so for n is equal to 10, let's say n is equal to 10, our indices would be from 0 to 9. So our root node would store the answer for the complete array. So our left child would store the answer from till midpoint 0 and 9. What is the mid of 0 and 9? It is 4.5. So let's take it as 4, the integer part. So it will store from 0 to 4, and remaining elements are 5 to 9. Right, till 4 we have. So mid plus 1 to end. So again, extending the same idea to this node, this array, this index will store, this node will store the answer for 0 to 2, right? And this for 3 to 4. This will store the answer for 5 to, let's say, 7. And this will store for 8 to 9. How 7? 5 plus 9 divided by 2 is 7. Till the midpoint, it's storing in the left part, and from mid plus 1 to end, it's storing in the right part. So this will store the answer from 0 to 1. This will store for 0 to 0. This will store the answer for 3 to 3. This will store the answer for 4 to 4. And this will store the answer for 5 to 6. So these are leaf nodes. These two are non-leaf nodes. So I need to extend the tree and create two more children. Okay. These are storing the answer for 5 to 5, 6 to 6, or 0 to 0, 1 to 1. Okay. So let's say, now let's count how many nodes you are needing. Right? For n is equal to 10, my guess would be 19 nodes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. 19 nodes. Now still the nodes come out to be 2n minus 1. Then why did I say 4n, right? So actually you are not using 2n minus 1 nodes. In the array representation, you have these useless nodes which are there in the memory, but you cannot use. Okay, so all these nodes have to be taken in the memory. So these are the nodes which are not being used. So there will be spaces in the array, right? If the array was like this, you had filled elements still here. These two values were stored at these two indices. Then there would be long gap, which would be these empty arrays, and then we would have these two values. So we would have empty gaps in the array corresponding to the leaf nodes which we are not using, right? So these nodes have to be included. So that is why I said the size would be 4n. So as for a formal proof, I think it's taking a lot of time, but I still dive into the proof. So when h is equal to 0, we had one element, one node, two node, four nodes, 8 nodes, and 16 nodes. Okay. So if I take the sum of all these nodes, right, I need to count these useless nodes, right? So the sum of all these nodes would be 1 plus 2 plus right up till 16. Or 16 I can write as 2 power 0 plus 2 power 1 plus up to 2 power 4. And 4 was what? The height of the tree. Height of the tree in the previous part, taking this from here. If I feed this value right here, 2 power 0 plus 2 power 1, right up till 2 power log n base 2 ceiling. This will be the number of nodes that I'm using. Okay. So this is basically a geometric progression. I hope everyone can see that with r is equal to 2. So if I quickly just write down the sum of this, it is a into r power n minus 1 divided by r minus 1. So using the same formula for here with r is equal to 2, which is our common factor, we end up with uh, how many elements are there? Like what is the value of n, or the number of terms? The number of terms would be 1 log n base 2 ceiling plus 1. Any doubt till here? I hope everyone can see that when power was 1, there were actually two elements and like that. So when the last element is log n base 2 ceiling, there are log n base 2 plus 1 elements. So putting the formula, we end up with 1 into r power n, or 2 power n being the number of elements. We have log n base 2 ceiling plus 1 minus 1 divided by 2 minus 1. So it is 2 power log n ceiling plus 1 minus 1. Okay. So expanding this. So log n base 2, I don't think I can solve this any further if I cannot expand this ceiling value, right? So when I'm writing bounds of any function, so ceiling of log n base 2, let's say ceiling of x will be between x and x plus 1. So I need to take a comfortable size, right? So I need the larger value. So replacing this with x plus 1, or I should write like this: size should be less than or equal to 2 power log n base 2 plus 1 plus 1 minus 1. I've just replaced this. I've just replaced this value with this value. Okay, right here for a larger bound. So equality has changed to less than or equal to. So if I just write down like this, 2 power 2 plus log n base 2 minus 1 will be 2 power 2 into 2 power log n base 2 minus 1. 2 square is 4. 2 power log n base 2 is n, 4n minus 1, which will give me 4n as a comfortable size of the segment tree which I can take. Okay, so size of segment tree should be clear. If there's any doubt, you can ask. Cool. So now we'll move on to the basic operations in a segment tree. So what was the previous problem that we were trying to solve? The previous problem we were trying to solve was of sum. Okay. But now we are using minimum maximum. Given an array A with n elements, we need to calculate the minimum or the maximum of elements. So for the purpose of explaining, I'll just use minimum. So minimum, I need to calculate minimum of elements in the range L to R for Q queries. So now this is n is equal to 8. I need to fill this segment tree. Okay. So we are basically trying to understand the three basic functions by doing this. The first basic function is a build of segment tree. The second function would be update of segment tree. And the third would be query. We have already discussed update and query in not in much detail earlier using the sum part, but now using the minimum, we will actually uh, discuss in detail. So I hope indexing of the tree was clear. For any index I, the left child would be 2i and the right child would be 2i plus 1. And we are following one base indexing for the tree. Okay, array is following zero based indexing starting from 0, but in tree we are using one base indexing. This is node 1, this is node 2, this is node 3, and so on. Okay, if this was node 5, this was node 10, and this was 11, like that, for clarity. So node 1 should store the answer for the complete array, but how can I fill this value if I do not know this value and this value, right? So I need to know the answer for this and this value. For knowing the answer for this value node, I need to know the answer for left and right node. So the using recursion, we actually create the tree recursively, but actually the values are filled in a bottom up fashion. And if you remember clearly, the leaf nodes are actually the array elements only. In the case of sum, in the case of minimum only, when leaf nodes basically store the answer for single element. So if you have the subarray like this is a subarray, and I ask you the minimum in this subarray, as it's just a single element, the minimum would be the element itself, right? So I can safely fill the values, leaf values, with the actual values. So we just fill the values: 4 minus 1, 9, 6 minus 2, 5, 7 minus 8. So now I have the value of this node and this node, so I can definitely fill the value for the parent node, right? So what would be the minimum of 4 and minus 1? What would be the minimum for 9 and 6? 6. 5 minus 2 is minus 2, and minus 8 is minus 8. So like that, now I can fill another level. Now I have the answer for this and this. Both of these children will return the value to their parent node, and the parent node will solve the larger problem. 6 and minus 1 is minus 1, minus 2, minus 2, minus 8, minus 8. So the minimum for the whole array is minus 8. So this is how build operation is performed. So time complexity is basically the amount of work done. Okay, in asymptotic notation. Asymptotic notation, if they are not clear to you, it's also fine. Asymptotic notation are basically big O, omega, and theta notations. You can search about them later on. But the amount of work done, okay, how much work did I do actually to create this array, create this segment tree, or fill our segment tree array? It is actually the number of elements only, right? So the number of elements in my segment tree is actually the number of nodes. So number of nodes is 2n minus 1, right? So I actually created 2n minus 1 nodes, and at each node I did some constant work. taking minimum, maximum, addition, all of these values are constant time operations, right? If you need the answer for sum for two elements, it's basically just a plus b. So addition, minimum, maximum, all of these are constant time operations. So build takes order of n time. Okay, order of n time. Order of n, how we are creating these many elements, and 2n minus 1 is basically just order of n, as we have done order of n work. So build operation in normal cases would take order of n. Actually, in some cases, this would also be multiplied by some constant, which I will discuss in a while. So if I want to update value at some index, let's say index 3. Okay, let's quickly write down the indices 0 to 7, 0 to 3, 4 to 2 to 3, 4 to 5, 6 to 7, 0, 1. So, so updating at any particular index. Let's say I need to update at index number 4. So I check I start with the root. I check both the left part and right part. The left part of the array 0 to 3, I do not need that, right? Index 4 is definitely on the right side. So I move to the right side. Index 4. Okay. Index 4 is definitely on the left side of this, right? 4 to 5. I do not need 6 to 7. So I move here. Then I move here. Then I update the value and I return. Okay. And I return the answer. I update the value at 4 index and then I return. So should I? Okay. Okay, I've already explained how updates actually occur. So I will not make an update right now. Updating at index actually made me go from the root right up till the leaf node. And in the worst case, the leaf node will be the deepest leaf, and the deepest leaf will be at a height of log n. Right? Height was log n. So height was log n. And I traversed total h work. I actually did a complete h work. So order of h would be my complexity for update, or order of log n base 2. This is the work done in update. As at each level, I'm only traversing through one index. Okay, now query. So query, let's say I want the answer for 2 to 6. Now while querying, there are actually three cases. Okay, I'll explain what. Let's say my the current index which I'm on is storing the answer for the this part of the array. Okay, so if I'm on this index, I'm storing the answer for 2 to 3. This is 2 to 3, and the range which I want the answer for is 3 to 5. So it is I want the answer for this range, but my current node is only providing me partial answer. Like I just need this part of the segment. So I need to make both calls to both sides. So I check for left side and I check for right side. So at this index, so total from an abstract level, there are three cases. The first case would be partial overlap. Second case would be no overlap. And the third case would be complete overlap. This is our best case. Starting from complete overlap, I think that would make more sense. So if I'm currently at this index, if I'm currently at this index and I want the answer for this, so definitely this is lies completely inside the range that I'm in. So this is the best case, and I can directly return without making further calls to the left and right child. If I am currently at index, if I'm currently at index which stores the answer for this part of the array, and I want the answer for this part, this lies completely outside of what I want. So I'll return some 0. Okay, if I'm calculating the sum, then this part of the array actually contributes nothing to my answer. So I can simply return 0, as 0 is the array for the right part. 0 is the sum for the part that I do not want the answer for. Then, if the case is something like this, I want the answer for this part of the array, and my current index is storing the answer for this part of the array. Then it is a partial overlap. So I need to check for left and right both. So I make two calls, one for the left and child and one for the right child. So I wanted the answer for this part. Let's say the left child hold the answer for this part. So it's a complete overlap. So it will simply return from here. And the right part holds the answer for this part, which is outside of my complete array that I want. Right. So this contributes nothing to my answer. So I contribute 0. So this was the case of partial overlap. This is the third case. This was the first case, complete overlap. This was the second case of no overlap. Okay. So 2 to what was my range? I was querying for 2 to 6, right? So 2 to 6. I start with the root node, 0 to 7. So 0 to 7 is the answer for the complete range, and I only need the answer for 2 to 6. So it is partial, right? So I need to make a call for left child, and I also need to make a call for right child. But first, the left child has to return his answer. So I check 0 to 3. 0 to 3 is also partially overlapping with 2 to 6, right? 2 to 3 part is actually the part that is common, the intersection of both the two. So I need to make a call for left child and right child both. So left child actually is 0 comma 1. So does 0 comma 1 have any overlap with 2 comma 6? 0 comma 1 is answer for this part, and 2 comma 6 is actually the range that I want. So it's the case of no overlap, condition number 2. So I can simply return uh, any, like, for example, here our problem was min max. So instead of returning 0, I should return some negative infinity value. Sorry, if you're calculating minimum, then I think I should return infinity. So I return something like int max from here. Okay, I'm returning you infinity. So even if you take minimum with infinity, you still end up with your actual value which you want, which will be returned from the right child. So now right child 2 comma 3. 2 comma 3 lies completely inside 2 comma 6, right? So 2 comma 3 lies completely inside 2 comma 6. So I can simply return the value of this node. So the value of this node is 6, and I do not make any further calls. Okay, so this node is returning 6, and then the parent returns 6 to its own parent. 6 is the value returned by the left part of our root. Now I check the right part. So 4 comma 7 is partially inside, right? So it needs to make call for left and right child both. So when it makes the call for 4 comma 5, it is partial. It is completely inside 2 comma 6, right? 2 6 and 4 5 are right here. So it lies completely inside this range. So we can simply return this value. So minus 2 is returned by left child. So minus 2. And what would the right child return? The right child has 6 comma 7. 6 comma 7 is partially overlapping with our range. So we make two calls, right? So our left call would return, it's a complete overlap. Okay, 6 lies completely inside 2 comma 6. So we return 7 from here. 7. And this would return infinity. So minimum of infinity and 7 will return 7. 7 is returned from the right part. So minus 2 and 7. What is the minimum of minus 2 and 7? Minus 2 definitely. So we'll return minus 2 from here. So 6 was returned from the left part and minus 2 was returned from the right part. So minimum of these two would be minus 2. So minus 2 is the answer for our complete query for 2 to 6. So let's check if that is the case. If I traverse from 2 to 6, this is the answer. This is the range that I'm checking for, right? And definitely the minimum is minus 2. So yes, the query function is working. So how much work did I do in query? Let's write the answer for update. So update took order of login time. In query, okay, so bear with me. If I'm making any query, right, there are three cases: complete overlap, partial overlap, and no overlap. In complete overlap, you are simply returning the value and not making any further calls. So 0 children are checked after this. In no overlap, 0 children are checked. In partial overlap, 2 children are checked, right? So if you are at two extremities of the range, you need partial overlap, right? So let's say there was a partial overlap at this part and this part. Okay, so there were two calls made at this height. So if you consider this to be like a pipeline in which you are doing some work, at this particular index, you traversed just one node, right? This node made call to two nodes. Now this node can make call to two nodes, but if it does, then this means that at worst case, this can also make two nodes, call to two nodes, right? So it's making call to two nodes. All of them are partial. 2 plus 2, 4. Now this is the limit. More than 4 nodes at any particular level can never be traversed. Okay, so if let's say the range was complete, the complete range, if you were checking for the complete range, then you simply return from these two indices, right? You do not go further. But if the range was like 2 to 6, which was something like this, okay, so you return from here and from here, sorry, 6 and from here. So at this height, you checked two nodes, and at this height, you checked just one node. So 4 is actually a very loose bound. At any particular level, it will be rare that you are checking 4 nodes. So the number of nodes being traversed at any particular height will be less than equal to 4. So and the height is total log n. So 4 log n is a good estimation of the total amount of work done for any query. And order of 4 log n will actually be order of log n. This is why the query takes order of log n time in the segment tree. Now, will any doubt till here? Tanshu, any doubt till here?
No, bhaiya, no doubt.
Okay, so we have discussed sum and we have discussed min max. So it's time to, I think, discuss a bit of code. Okay, so this is a template form of code. We have created a class and segment tree. You can simply just declare this globally if you want. It will still be fine. Okay, so you resize this to 4n. 4n was the size that we derived mathematically in previous section. Now the build operation. There were three operations, right? The first one was build, which was an order of n operation. Update and query each took order of log n time. So there was one important thing that I missed. Okay, whenever you are creating a segment tree, there are two things which you need to create, which you need to keep in mind. The first one would be, what is each node storing? Okay, what is each node storing? So in our first case, the sum part, each node was storing the sum for particular segment. In our min max query, we were storing the sum, we were storing the minimum of a particular segment, right? So we need to keep in mind what is each node storing. So here we are simply just storing sum or either min max. So it is an integer. So the segment tree is of type integer. And second, what is the operation that is being performed while merging? When we are making call for the left child and right child, after returning the answer from their further children, they need to return the answer as well to the parent. Now parent has to merge the two. Okay, so what kind of operation is being performed? So basically operations like plus, minus, multiply, divide, XOR, all of these operations are constant time operations, order of one. So this was what I'm talking about. This is what I was talking about earlier. Each node is storing just a single integer, so it was pretty easy for us to create a segment tree using integer, just single value. So in the build part, it's basically just a DFS traversal and creating node at each step. So we find out there are basically multiple parameters, three parameters: starting, ending, and cur. Cur is the index of our segment tree. So the root node was 1. Okay, and here we are computing 2 into cur and 2 into cur plus 1 as the left child and the right child after computing the mid. So starting till mid was the answer to our left child. Mid plus 1 to end was the answer for our right child. So we make two calls for the left part and the right part for building the segment tree. After they have returned, right, this was the part they have returned. Now they have returned their answer. Now these two answers have to be merged, right? So segment tree of 2 into cur will actually have the correct value of the left child, and segment tree of 2 into cur plus 1 would have the value for the right child. Now since the query was minimum, we perform the minimum of the two values, and minimum is a constant time operation, so it will not multiply the complexity with anything large, right? So segment tree of cur, which is our parent, is the minimum of left child and the right child. This is the part which is this is the most important part and the crucial step, which is actually you performed an update and query as well, right? See this part and this part. So this was our first part, build, which is an order of an operation. Now updating is very easy. We just make call to one child. Okay, if index, let's say at index idx we want to put the value val. Okay, at array of idx we want to put the value val. So we need to make some corresponding changes while returning, right? Like when we're returning from the two nodes at the parent, we need to make changes, right? If this value was changed, then it is possible that this value also has to be changed. So this is what we do. We make just one call, either to the left or to the right. And our base case was actually this st equal n, which means we have reached a leaf node. This means a leaf node. And in our case, a leaf node is basically just a single element. So we put array of st at segmentary of cur, which is our leaf node. So in update part, we just make a call to either left or either right. And accordingly, we make changes to our parent. Okay, and here we have updating the value at the index when we reach the leaf node. Because see, idx, the index is an element in the array, right? So it's a single element, and single element we all know is stored in the leaf. So we need to go to the deepest of leaves to make the change. This is our point update. Okay, there are two types of update actually. There is also range update, for which you need to know lazy propagation, and I don't think we'll be able to cover this in this session. Maybe in later session we'll discuss range updates and lazy propagation. So query, there are three cases. First is the no overlap, complete overlap, and third is the partial overlap. In partial overlap, we make two calls to the left and right. Okay, so in no overlap, our range was L to R, for which we wanted the answer. Okay, L to R, and currently we are at ST to EN. So we are storing the answer from ST to N in our in index cur. Cur is the index of segment tree, and L and R are the indices of our array. So if R is less than ST, okay, if or if ST is greater than LR, so let's say our L and R was this, we want the answer for this, and ST is greater than R, which means we are ahead of this segment. Or if EN is less than L, which means we are behind this L, okay, L value. So which means we are completely outside of this range, right? These two values are completely outside, so they do not contribute anything to our answer, but we still need to return something, right? If it was the case of sum, so we would have returned 0, 0 in case of sum. But since we are calculating minimum and we do not want these values to affect our actual answer, so we return int max, which is our infinity value. So taking minimum with infinity will actually return you the number itself. Okay. And complete overlap. Let's say we are completely inside this value with this range, right? So we can simply return the value. So we simply return segmentary of curve from here without making any further calls. Now comes partial overlap. The case when it is something like this. Our range is this, and our ST and EN are something like this. So we need to check both the parts. So we make a query to left, we make query to right. We are returned an integer and we return the minimum of it, returning us the answer to this L2R query. So in worst case, we did 4 log n work, which was basically just order of log n time. And when n is large, this will actually save us a lot of time. Okay, so I think we have reached the R mark. There's just one last use case which we're going to discuss, and then we'll end the session. So till now, we discussed two problems, was sum and one was minimum. And both of these operations were actually constant time operations. And at each index, we were just storing a single value, a single integer. But in this case, we will need more than that. So the problem is, return me the maximum subarray sum in the range L to R. So I'm not talking about the maximum subarray sum in the range L to R. Okay, we'll discuss this at a very broad level. Okay, just explain the problem to you. 3, 4, 5, 6. Okay, -5, -1, 2, 7, -1. Okay, so if I ask you what is the maximum subarray sum, so subarray which I can directly see is this. This is the subarray which is going to return me the maximum sum. 7 plus 3, 9. 7 plus 3, 10 plus 2 is 12. So 12 is the maximum subarray sum. But if I ask you what is the maximum subarray sum, let me just write down the indices. 0, 1, 2, 3, 4, 5. If I ask you what is the maximum subarray sum in the range 1 to 3, then what would be the answer? That means I only want you to consider this part of the array and tell me the maximum subarray sum. The subarray which I can see is this 2 to 3. So this is different from the answer that we got earlier. So this is the answer will be 5. The answer will be 5. In this range, the maximum subarray sum would be 5. So how do we get it? If you think closely, if I ask you the subarray sum in this part, this will actually be the subarray sum of these two and the maximum, right? Or is it something different? I think the answer is a little different. The case can be if the subarray was something like this. Let's say the maximum subarray in this range was something like this, like this is the maximum subarray, and I want the answer to this. Then this will completely be in the left part. So I can simply take the maximum of left and the maximum of right and return. It would still give me this. But what if there was a slight overlap? Let's say the subarray of my larger problem was this, and half part of it is in here, in this part of the array. Oh, sorry. In this part of the array, and the other half is in this part of the array. Okay. So while merging, I cannot simply just take the minimum of maximum of the two sides. I need to also check for this case. So there are three cases. The first one is completely left, completely left. The second one is completely right, and the third one is middle. So what all do I need in my array? I actually need three things. I need the maximum sum for the left part. I need the maximum sum for my sorry. I need the maximum sum. I need the suffix sum maximum. I need the maximum prefix sum. So for this half of the array, this part was common, right? And if I just calculate for this part of the array, if I magnify this and keep it here, let's say this part was overlapping. So the maximum suffix sum is what is overlapping, right? So we need to consider this as well. So while combining, the maximum sum of parent would be maximum sum of parent would be the maximum sum of left child, the max of three things. Okay, max of left child, maximum of left child, max of right child. These are the first and second cases when the maximum sum completely rise to the left side and the right side. And when there is a slight overlap, we need the sum of these two. Maximum suffix sum of left added with the maximum prefix sum of right. Adding these two values will give us the common part, this actual intersection part, which will be the answer to our query. So to calculate this, we will also need one more thing. We will also need total sum. So earlier we were just storing a single integer as the segment tree, right? Of some size 4n. But now we'll need a custom class as we are storing 4 members. So let's jump onto the code. So here we have 4 things in a particular node. Earlier we had just one integer. Now we need to store 4 things. One is the maximum sum, one is the prefix sum, and one is the suffix sum. I'll talk about total sum and why we need it in a while. I'm not using the template part of the code. I'm just simply declaring a global array named segment tree and using it. So in the build part, we have reached this is the base case when we've reached a leaf node. For a leaf node, if there's just a single element, then prefix sum, total sum, maximum sum, and everything will be just that element value, right? We'll put that and we'll return. But when we are calling to the left child and to the right child, I'm actually getting copy here. Okay, I'm calling to the left child, I'm calling to the right child, and I'm storing their values here. So now I have the sum for left and right. So total sum of parent would be the total sum of left and right child. Okay, this is a no-brainer, absolutely. So total sum is actually, so TS is basically total sum. I've created preprocessor directives for this. Total sum for the complete parent would be total sum of left and total sum of right. Cool. Maximum sum. This considers 3 cases. One when the maximum sum lies completely in the left child, like this. In the completely in the right child, like this, or a part of both the two. Okay, so left child is the first case, second case, and the third case. When suffix sum plus prefix suffix sum of left child and prefix sum of right child will be added. This is the suffix sum. This is the prefix sum of right. So both of them have to be added and taking the maximum as the maximum of parent. Okay, then prefix sum. So the reason I took total sum is will be more clear right now. So when we are taking a prefix sum for this value, there are two halves. Okay, so let's say the prefix sum is only this part. So it will be prefix sum of the left child only. Okay, but if the prefix sum is something like this, overlaps complete the left child and a little part of the right child. So it will be the total sum of this array added with prefix sum of the right array, which we have done here. Total sum of left plus prefix sum of right. So these are constant time operations, like order of operations. 1, 2, 3, 4, all of these four. So we're actually performing constant time operation only. This might seem like a lot of work, but this is actually constant time operation only. And you're feeding it back. The same logic is applied at query as well, and we are able to come up at the larger problem. Cool. So this is a homework problem. I'm attaching the link to it in the comment section. You can check out these two links. The first one is a problem which was created by us. It involves usage of segment tree, and here the type of segment tree would be bit set. So you need a slight knowledge of bit sets as well. So let's say the bit set size is W. This actually has to be a static value. You cannot just create a dynamic value. Bit set of W and create a segment tree of this size, okay, 4n. So the complexity of each operation, which I was talking about earlier, the merging part. The merge part was earlier addition, subtraction, XOR. All of these were order of one operations. But when you're merging using bit sets, right? So it will be an order of D by 32 operation. Why D by 32? It actually depends on the architecture which you're working on. It can be D by 64 as well, but it is preferred to take D by 32. So in our problem, the range was up till 1000. So D by 32 comes out to be a very small value. So this was the constant which was multiplied by all the uh, queries. So to summarize it all, when you're working with segment trees, build operation takes order of n time, and each of the queries take log n time. This is the overall complexity of your solution when you're using segment trees. With this, we conclude the session. If there are any doubts, you can ask.
Thank you, Abhishek sir, for the splendid session, and everyone for tuning into today's session. I hope you found it informative and enjoyable. Until next time, keep learning, growing, and pursuing your passion.